So in this video, we have an interesting look at some problems involving optimization. Okay, so optimization is the practice of taking an equation and trying to determine what the maximum value is, or what the max or minimum value is. So if you think about it like this, when you go to the grocery store, sometimes you look at a bottle of ketchup or a bottle of any other good. And you sometimes I don't know. Maybe I'm just a big geek. I wonder, why is this shaped the way it is? Okay, so um, a lot of times companies will, when they produce a product, one of the things that they have to keep in mind is, how am I going to distribute my product? So not only do I want to be able to maximize the amount of product I can give to the consumer, I want to make sure that I can make the most of the logistical side of my business. In other words, I've got to get this product to market. When I hire a truck driver, I don't want to have to pay. I don't want to have to pay an exorbitant amount of money to ship a small number of goods. So there's a whole lot of what is the best way to do this that goes into companies' decisions. That idea is called optimization. How do I get the most out of my circumstance? Or it could be the least. You want to minimize certain things. So how do I minimize this parameter of my business? Okay, so if you think about what we've done with derivatives lately, we have taken those things and set them equal to zero so that we find critical points. And the important thing about a critical point is that is where a maximum or a minimum occurs. Let me show you right here exactly what I mean. Now we did this, and just to drive home the point of what we just came out of, is the idea that we have a graph here, right? And I have this function that looks a little bit like this, okay? Well, this point right here, okay, this point is called the local max. That local max occurs at an x value, and it is a y value. Okay, so it occurs at an x value, but it is a y value. And sometimes our book refers to this x value as a c value. Okay, we call that a c value because it's a critical point. It's where the derivative, where the slope of that tangent line is equal to zero, right? That's a real big deal. The slope of that tangent line is equal to zero. In these problems, we're talking about how to maximize profit. In another problem, we're going to talk about how to maximize revenue. So let's think about what we mean when we say profit and what we mean when we say revenue. Okay, so revenue is the money that we bring in. Okay, money generated. So my mother-in-law makes these fantastic pepper jellies and all this kind of stuff. And, it cost her a certain amount of money to make those, but then she can sell them for, I don't know, $8 a jar. Okay, so if she sells 100 jars at $8, her total revenue is $800. But the thing about that is, it cost her a little bit. She doesn't keep all $800. She has to subtract out her cost. Okay, so these are the two functions we're going to be focusing on today: revenue, okay, and profit. So our profit is found when we take the revenue and subtract the cost. So let's take a look at this problem and see if we can figure out what we're doing here. We have a revenue function of 4498x, and a cost function is given as x cubed plus 647x squared minus 2641x. Okay, and in this case, x is the number of items sold. So for my mother-in-law, it's the number of pepper jellies sold. What's the maximum possible profit? In other words, we want to maximize profit. Well, if that's the case, we want to go in and take the derivative of profit, right? To maximize profit, we have to find r prime of x. Set that equal to zero, find the critical points, and then that's going to help us identify how many items we should sell. So our profit function is the revenue function. This is our revenue function minus the cost function. And so we can simplify that and then take the derivative. So if you take the derivative of P of X, you get this thing here, okay? To solve this one, we have to use the quadratic formula. So on the next slide, let's take a look at what that looks like. Let me go back right quick. In this case, A is -3. We're going to combine some like terms. B is -1294 and C is 7139. Now notice we had to distribute that negative, and that's how C wound up being so large here. Here's where I do the quadratic formula. So if you have any questions on this, then you need to take a look at kind of what's going on, just to make sure you can get the right numbers. From my quadratic formula, I get these two values. Doesn't make sense to use that negative value, right? We're talking about the number of items sold. So I'm just going to forget about the negative value, and we're going to focus only on the 5.448. It really isn't possible to sell 5.448 units of goods, right? Well, what I need to do is see how much profit will I get from selling 5 units and how much will I get from selling 6 units. So I'm going to go and I'm going to evaluate the function at 5 and evaluate the function at 6, right? In other words, when I say evaluate the function, I want to know I'm evaluating the profit function. You can double check my numbers, but it looks like we're going to get the maximum profit at 5 units, which would be a substantial amount of money. The profit at x equals 5 is greater than the profit at x equals 6, right? So the maximum profit is $19,395. It's always helpful if you can identify a process, right? So if we take a look at this process, then we've got identify the equation we're optimizing, find the derivative, set it equal to 0, and then we're going to evaluate the function in step 1 at the endpoints. Now, it really depends on what your problem is, whether or not you have endpoints. In example 1, we did not have any endpoints. In example 2, though, I'm going to have some endpoints. Let's take a look briefly at this example. Owners of a canoe rental company charge between $8 and $31 per day for canoe rentals. The number of canoes rented per day can be modeled by the linear function, this thing. Okay, you can imagine that if you charge $31 a day to rent a canoe, then there's not going to be as many people renting them as it would if you only charged $8 a day. Okay, so the price that you charge for those canoes is really determining the demand you have. We have to look at a range for which the owner wants to rent the canoes. In this case, our range is 8,31. We want to go in and find out what the critical points are for this setup, right? But our thing is we've got to maximize the daily revenue. Our daily revenue would be the number of canoes rented times the price that you charge. So we're going to take our revenue function and we're going to have N of P times P. And if I distribute P, I can go in and find the derivative. I get 155 minus 10P squared. Or excuse me, 10P. I did the 10P squared a minute ago when I was creating my notes on this. So if I write the revenue function out, it looks like this. 155P minus 5P squared. And if I take the derivative, I get this. Let's talk about how to go in and figure out what's going to make this equal to 0. It looks like P is 15.5. Now this is different than the number of canoes, right? The number of canoes turned out to be 5.448, but I can't have 5.448 canoes, right? In this case, P is how much I charge, and I can charge $15.50. Okay, so I don't have to look at 15 and 16 on this case. I use 15.5. To figure out the biggest revenue, I've got to plug those endpoints into the revenue equation, and I also have to plug in that guy right there, 15.5. I think you can see from the numbers that 120125 is the largest amount of money that I can bring in. So the maximum revenue is 120125. You've got a few of these to take a look at in Newton. We're working pretty good piece into the term now. So if you haven't figured out, I'm here. I'm helping. Let me know what videos you need so that I can give you that individualized help.